Okay, let's unpack this incredible global quantum race. I mean, we've heard about the theory for decades, right?
Oh, absolutely.
But now it feels like we're really in the engineering phase. Companies are actually building machines, pouring billions into it.
That's right. And the core concept, the thing you really need to grasp to understand this shift, is the qubit. It just fundamentally changes computation.
Right, not just 0 or 1 like our normal computers.
Exactly. A classical bit is strictly 0 or 1. A qubit, though, exists in superposition. It's kind of like being both 0 and 1 at the same time.
And then there's entanglement.
Yes, entanglement. That's where the state of one qubit is instantly linked to another, no matter the distance. Combine that with superposition, well, you get a system that can explore a huge number of possibilities all at once, exponentially many.
So for our deep dive today, we've got this interesting mix of sources. On one hand, these really aggressive corporate roadmaps, Google, Microsoft, the big players.
Yeah, very ambitious timelines.
But then we've also got these, let's say, deep academic critiques. Sometimes quite scathing, actually.
Grounded in the physics.
So our mission here is to try and, cut through the hype a bit, distill what's actually happening now, who's leading, which technologies matter, and crucially, where are the big technical hurdles still.
And that's the real tension right now, isn't it? The gap between achievement and actual utility. We've hit these milestones like quantum advantage or quantum supremacy.
Where they've beaten a classical supercomputer on some specific task.
Exactly. Highly specific, often very contrived tasks. But what they are absolutely not yet ready for is, practical, real-world stuff. Everyday applications. That gap it's huge. It's everything right now.
Okay, so let's dive into the front lines then. The hardware itself. Because it's not like there's one standard way to build a quantum computer. It's a really diverse landscape.
It really is. Lots of different approaches being pursued.
So what's kind of leading the pack? At least in terms of, say, technical specs right now.
Well, probably the most established approach uses superconducting circuits. That's what Google and IBM are heavily invested in.
Right.
The big trade-off there, they need extreme conditions. We're talking serious refrigeration, cryogenic temperatures near absolute zero.
How cold are we talking?
About 20 millikelvin. Just incredibly cold. To keep those superconducting qubits stable enough to operate, it requires massive cooling infrastructure.
And Google's been putting out some, frankly, jaw-dropping numbers for their chips recently. They had this Willow chip, right? 105.
That's the latest, yeah. State of the art.
And they're reporting fidelities like 99.97% for single qubit gates. I mean, how close is that to what we actually need for useful computation?
It's spectacular progress, no doubt, but it's still short of what you need for true fault tolerance, which we'll definitely get into. But those numbers, 99.97%, and importantly, 99.88% for the entangling gates, which link qubits. That's pretty much best in class right now for that technology.
Okay.
And they use that fidelity to run something called the quantum echoes algorithm. This was a big deal because they claimed it placed the results concretely beyond what classical computers could simulate or verify easily.
And what did that actually involve? What scale are we talking about?
Well, to verify that they'd actually achieved that advantage, they had to perform, get this, 1 trillion measurements.
1 trillion. Wow.
Yeah, so it was a successful demo of advantage, but again, for a very specific engineered task, not something you'd use for, say, drug discovery tomorrow.
Right. Okay, so let's contract that superconducting approach with the trapped ions camp. Companies like IonQ, Quantinuum, Oxford Ionics is in there too.
Different physics entirely.
They're using electromagnetic fields to hold individual atoms, right? Single particles.
That's the idea. Traps single-charged atoms ions using lasers and electric fields.
Is the trade-off here maybe better fidelity, even if the qubit counts are sometimes lower?
Generally, yes. Ion traps tend to produce qubits that are, let's say, cleaner, more stable, and often better connected to each other. So Oxford Ionics, for instance, is really pushing for ultra-low error rates. Their target is that magic 99.99% fidelity, 4 nines for systems with, say, 16 to 64 qubits. They use their own proprietary electronic control system for that.
Okay.
And then you have IonQ. Their focus is interesting. They talk a lot about algorithmic qubits.
What does that mean exactly? Algorithmic qubits.
It's about the quality of the computation you can actually perform, considering connectivity and fidelity, not just the raw number of physical qubits. They're aiming for what they call broad quantum advantage by 2025 based on that metric.
So quality over just quantity.
In a sense, yes.
And then we've got completely different approaches still finding niches, like neutral atoms. Pascal is a big name there.
Right, using uncharged atoms held by lasers. Pascal's roadmap is really focused on scalability. They're talking about aiming for 10,000 qubits by 2026. That's a huge number.
10,000? And what about annealing, like D-Wave? That's different again, isn't it?
Very different. D-Wave focuses specifically on quantum annealing, which is tailored for optimization problems. And here's the key thing. They are already providing commercial value. This isn't just promise, it's happening now.
Right. I saw that example with the Pattison Food Group, the grocery chain.
Huh?
They use D-Wave's, what was it, the Advantage 2 system?
Yeah, the 4,400 qubit annealer.
And they reported an 80% reduction in the time it took to do their scheduling. So, okay, quantum utility isn't maybe cracking encryption on day one.
Definitely not.
It's optimizing grocery logistics.
Yeah.
Or maybe salad dressing placement.
Well, maybe. But it's a crucial point for setting expectations. Targeted commercial value is possible today with certain types of quantum hardware for specific problems.
Okay, so that's kind of the now. Let's shift to the next, the roadmaps. Here's where it gets really interesting, right?
This is where the ambition really rounds up.
Because the big goal shifts from just showing us supremacy on these contrived problems to actually building reliable, fault-tolerant machines that can solve useful things.
Exactly, and making that leap to fault tolerance, well, that's the Mount Everest of quantum computing. It's incredibly difficult.
So what are the timelines looking like Google's aiming for?
Google's target is a useful, error-corrected quantum computer by 2029. They're building on that Sycamore supremacy result from 2019.
Okay, 2029 seems ambitious, but maybe plausible. But Microsoft, their roadmap seems almost radical.
It is. They're betting heavily on topological qubits.
Right. I read about this. They're planning to introduce this Majorana 1 processor early next year, 2025.
That's the plan. And they project this approach could scale eventually to 1 million qubits.
1 million? Why is this hardware so different? What makes a topological qubit special?
Well, the core idea is fascinating. Instead of just trying to shield a fragile quantum state, they're trying to encode the information in the topology of the system itself. Think of it like braiding ropes. The information is stored in the pattern of the braids, which is physically robust.
So the protection is built in almost.
That's the hope. They use these exotic quasi-particles called anyons, and the quantum information is stored non-locally in their relationships. In theory, this makes the qubit much more resilient to local noise and errors. It's hardware-level protection.
Okay, that's a very different path, if that works.
Wow. If it works, it could be a game changer for scaling. But it's also proven incredibly difficult to physically realize and control these Majorana modes.
Now, connecting back to the ion trap, folks, Quantinuum is also aiming high, right? Fault tolerance by 2030.
Yes, universal fault-tolerant QC by 2030 is their goal. They're currently at 56 physical qubits, but significantly, they demonstrated 12 logical qubits earlier this year.
Logical qubits, so that's qubits with error correction built in using multiple physical ones.
Exactly. And they achieved 3 nines fidelity, 99.9% on those logical qubits. That's a really important step towards showing that error correction can work in practice on their platform.
That sounds like solid progress.
Yeah.
And you have leaders like Sundar Pichai at Google saying quantum's arrival is, 5 to 10 years away?
He did say that. And Bill Gates, looking at Microsoft's work, I assume, sees practical uses maybe even sooner, within 5 years. The pressure is definitely on.
And we shouldn't forget the cloud providers here. Amazon with AWS Bracket, their strategy seems different again.
Right. Amazon isn't necessarily building their own universal quantum computer, at least not yet. They're focusing on being the cloud platform, integrating hardware from partners like IonQ, Rigetti, Oxford Quantum Circuits.
Providing access.
Exactly. And they're launching their own chip, the Ocelot chip, early 2025 as well. But its goal is interesting. It's designed specifically to help reduce the cost of error correction by up to 90%. They're tackling the economics and integration side.
Okay, which brings us neatly to the maybe the elephant in the lab. This massive gap between what we have now and what we actually need.
The NISQ to FSQ gap. Yes.
Right, let's break down that jargon. NISQ is?
Noisy intermediate scale quantum. That's where we are now. We have quantum processors with tens, maybe hundreds of qubits, but they're noisy, error prone. Intermediate scale means not yet big enough for the really big problems.
And FSQ is the dream.
Fault-tolerant application scale. That's the goal. Machines with enough high-quality, error-corrected qubits, logical qubits, to run algorithms that solve real, valuable problems. And the road between SQ and FQ is, well, it's long, hard, and very expensive.
What makes it so hard? What's the fundamental barrier?
It comes back to decoherence. Qubits are unbelievably fragile. Any interaction with their environment, heat, vibration, stray electromagnetic fields can cause them to lose their delicate quantum state. Poof, the information is gone or corrupted.
Yeah, it's the noise.
That's the noise. Maintaining that quantum state, the coherence, long enough to do a complex calculation, is the single biggest hardware challenge. It's why they need those crazy low temperatures and extreme isolation.
So how do you fight the noise? What are the strategies?
Broadly, there are two main approaches right now. The long-term solution, the one everyone agrees we need for FASQ, is quantum error correction, or QEC.
Okay.
This is where you use redundancy. You take many noisy physical qubits and encode the information across them in a clever way to create one much more robust logical qubit. If one physical qubit gets an error, the code lets you detect and correct it without disturbing the overall logical state.
But the overhead, we hear about this massive overhead. How many physical qubits does it take for one logical one?
It's enormous. The exact number depends on the quality of the physical qubits and the algorithm. But estimates for something like factoring a large 2048-bit number using Shor's algorithm, the kind of thing that breaks current encryption, suggest you might need around 3 million physical qubits to implement the necessary logical qubits.
It's a million.
And even then, the calculation might take something like 5 months of continuous operation.
Wow. Okay. 3 million physical qubits just to protect one complex calculation. That really puts the current 100-ish qubit machines into perspective. They're nowhere near that yet.
Not even close. It shows you the scale of the engineering required for QEC.
So if QEC is the long-term goal but requires millions of qubits, what are people doing now with these NIQ machines?
They're using the alternative. Quantum error mitigation, or QEM.
Mitigation, not correction.
Right. QEM doesn't use any extra physical qubits for encoding. Instead, it tries to estimate and subtract the noise computationally. You run the calculation many, many times, analyze the result, and use clever statistical techniques to try and filter out the errors and get a more accurate answer.
So you kind of brute force the accuracy by just taking way more measurement.
Essentially, yes. You increase the sampling overhead dramatically to boost the signal over the noise.
But there's a catch, right?
There's a big catch. The number of extra measurements you need, that sampling overhead, scales exponentially with the size and complexity of the quantum circuit.
Right.
So QEM works okay for small, simple circuits on today's NISQ devices. But as soon as you try to run a larger, more complex problem, the kind you'd actually want to solve, the number of measurements required, becomes astronomically large, like longer than the age of the universe large. It just doesn't scale.
Okay, that's a pretty stark limitation. A harsh but necessary dose of reality, maybe.
It is. And this fundamental noise problem and the limitations of QEM is why you hear so much skepticism from the academic community.
Right. I saw one quote from a physicist basically saying that for actual real-world applications, current quantum computers are, how do they put it? Good for absolutely nothing.
That's blunt, but it captures the frustration with the gap between the hype and the current reality of NISQ machines for practical problems.
So that skepticism needs to be part of the conversation.
Absolutely. To get past NISQ and towards real utility, we need to bridge that gap. People talk about moving through different regimes based on the number of reliable quantum operations, or QOPs, you can perform. Yeah, quantum operations, moving from NISQ, where reliable operations are limited, into the megaquop regime, millions of reliable operations, then gigaquop billions, and eventually teraquop trillions of reliable operations. That's seen as the path to real computational power.
Okay, so mega, giga, teraquop. That's the ladder we need to climb.
That's a good way to think about it. It's a measurable path towards utility.
But even with the hardware challenges, the industry isn't just sitting still, right? They're building the software stack already.
Oh, definitely. There's a huge amount of work going into the software tools needed to actually program and use these machines whenever they become powerful enough.
We see things like IBM's Qiskit.
Yep, based on Python, very modular, widely used for building circuits.
And Google has Cirq, also Python-based. Is that more focused on the current NISQ machines?
Yeah, Cirq gives you quite fine-grained control, which is useful for experimenting on today's noisy hardware and developing error mitigation techniques.
And then Microsoft has Q-Sharp. That seems different again.
It is. QStag is a standalone, high-level language designed more with scalability and fault tolerance in mind. It integrates well with classical computing for hybrid workflows, so you see different philosophies even in the software.
And all this software effort points towards the why, right? The actual applications people hope to run eventually.
Exactly. Where is the payoff expected? The most promising area, arguably, is simulation.
Simulating quantum systems themselves.
Precisely. Quantum mechanics is incredibly hard for classical computers to simulate accurately once you get beyond simple systems. So areas like quantum chemistry, designing new materials, understanding catalysts.
Like that Haber process example for making fertilizer more efficiently.
That's a classic example. Ammonia production via the Haber-Bosch process consumes a huge amount of global energy. If a quantum computer could help find a more efficient catalyst by accurately simulating the quantum interactions, well, that would be massive.
Huge impact. Okay, simulation is one.
Yeah.
Then there's the big one everyone talks about, cryptography.
Yep. Shor's algorithm. If you can build a large enough fault-tolerant quantum computer, Shor's algorithm can efficiently factor large numbers.
Which breaks most of the public key encryption we rely on today. RSA, Diffie-Hellman.
All vulnerable. That's why there's such a massive global effort underway to develop and standardize post-quantum cryptography, new encryption methods believed to be secure against both classical and quantum computers. It's a race, really.
A race against a machine that doesn't fully exist yet, but could.
Exactly. And then the third big area is optimization and machine learning.
Using quantum effects to speed up finding the best solution among many possibilities, or maybe training AI models faster.
That's the hope. There are quantum algorithms for optimization problems and ideas for quantum machine learning, but this area is also quite challenging. There are theoretical hurdles like barren plateaus, essentially, situations where training quantum algorithms becomes incredibly difficult. It's promising, but maybe further out or more complex than simulation.
So for any of these applications to really deliver, they need to hit that sweet spot, right? I think I saw this criteria mentioned.
Yeah, the trifecta. The problem needs to be quantumly easy, meaning there's a known quantum algorithm that offers a speed up, classically hard, meaning our best classical computers struggle with it, and crucially, practically useful, meaning solving it actually provides real-world value.
Quantumly easy, classically hard, practically useful. That sums up the challenge perfectly. Finding problems that tick all three boxes and then building the hardware to run them.
That's the quest. We know some things that are theoretically possible. We know the hardware is incredibly hard, and we're waiting for those three circles to overlap convincingly as we climb towards that TerraQuap regime.
So what does this all mean for someone listening right now? How should they think about this?
I think the key is to recalibrate expectations. Quantum utility isn't going to be like flipping a switch. It won't be a single sudden revolution.
Right.
It's much more likely to unfold gradually. We'll see progress through these phases, NIST, then hopefully megaquap, gigaquap, teraquap capabilities driven by continued, frankly, brutal advances in both the hardware engineering and the theoretical algorithms needed to cross that huge NIST to FISQ divide. It's a long game.
Which actually brings us back to one of the original computer pioneers, John von Neumann. He made this fascinating observation back in, 1945, when electronic computers were just being invented.
Oh yeah, what did he say? He predicted that the most important future uses of computers would likely be the ones they couldn't possibly predict then, simply because they were the furthest removed from what was feasible at the time.
That's a great point. The truly transformative applications might be things we can't even imagine right now.
Exactly. So if that holds true for quantum computing, maybe the ultimate prize isn't just breaking codes or optimizing logistics, as important as those are. Maybe the real revolution will come from applications that are literally inconceivable today, given the limitations we're still wrestling with, that unknown future. That might be the real potential here.